So far what we've been doing is determining the probability of events or outcomes given conditions. Probability, for example, of a wrinkled pea bearing plant given the condition of a selfing of an individual that's heterozygous. Okay, so you have a condition and then you have an outcome. Okay. But sometimes it's a little bit different. Sometimes you actually have an outcome and that tells you something about the condition. Let me tell you what I'm talking about. Now in the scenario that we already discussed, where you take an individual that has individuals that have this genotype, okay, and you cross them and you produce a round pea bearing plant. And you cross this individual to an individual that has this particular genotype. Okay? Remember what we already calculated? We calculated the probability that this individual has this particular genotype is equal to a third. Probability that this individual has this particular genotype, heterozygous, is equal to 2/3. And remind yourself why that is. Now, if we cross this individual, okay, this is the sort of probabilities of these genotypes. But if we get an outcome like this, then this revises what we think the condition of this individual's genotype is. And the reason is because you can't get this outcome if this individual has that. So what we can do is actually we can revise our probabilities. We can actually say, well, no, it had to have been this particular genotype because it's the only way that you can get this particular outcome. Now imagine another scenario. Imagine, in fact, that you actually produced in round pea bearing plants, okay? Which, you know, by definition, since this is a test cross, would have to be big R, little r. Okay? And you did it again, and you got this genotype again. And you did it again, and you got this genotype again. Actually, you did it again and again and again and again and again, and you never, ever, ever got wrinkled peas. Well, what would that tell you? Well, it would tell you that you'd really think that this is more likely. But, you know, maybe there's some small chance that this individual is of this, but it just happened to be, through a very rare chance, that it never transmitted a little r allele to its progeny. Well, you would, you know, depending on how much the outcome is, you might want to even bet a little bit on that. And what I'm going to tell you now is how to calculate these exact probabilities to determine if you were of the betting kind, and you had 10,000 bucks, then you could figure out what the probabilities are. So what we're going to do is we're going to calculate a particular thing, but before I do that, I need to give you a derivation of something called Bayes' rule. Okay. Now, let's just think about two different things that could happen. Let's just call them A and B. So A and B. Okay. Now, if we wanted to say what is the probability of A and B happening, well, if you think about it for a second, that would basically could be given in two different ways. You could say the probability of A and B happening is the probability that A happens given B has happened times the probability of B happening. Okay. But you could rewrite this differently. You could actually say the probability of A conditional on B times the probability of B, since these is going to be the case of probability of A and B, is going to also be equal to the probability of B given A times the probability of A. Okay. And you can think about for a little bit why that is going to be the case. Now, if we do a little bit of algebra, well, not very much, in fact, you can change this to say that the probability of A given B, okay, divide here, is equal to the probability of B given A. That's interesting. Times the probability of A divided by the probability of B. Now, we can further decompose this probability of B into all the different ways in which B can occur. And one way in which you can decompose it any way, but using the law of total probability, one possible way is saying that it's equal to the probability of A given B equal to probability of B given A times the probability of A divided by, okay, again, what we can do is we can turn this, the probability of B, into the probability of B given A times the probability of A. Okay, this is one way in which you can get B conditional on A having happened. Okay, or you could say the probability of B plus given A excuse me, given not A times the probability of not A. Okay? Remember what I've said is the A, probability of A plus the probability of not A, sum to 1. And what we've done is we've decomposed the ways in which B can happen under the conditions in which it happens with A having happened or with not A having happened. You can break this down even further. You can say, you know, the probability of B given A times the probability of A sub 1, you know, and then A sub 2, and then A sub 3, as long as all of these particular parts of this will sum to 1 based on the law of total probability. So let me simplify that a little bit. Let me rewrite it one more time for you. And I'm going to show you how this sort of hairy equation can be used to calculate things that are the probabilities of conditions already being the case dependent on the outcome. So I'm saying that the probability of A given B, okay, in this case B is going to be the outcome, and this is going to be the condition. Okay, this is the outcome, and this is the condition. It's a little weird, and you'll see why. Well, you already know why, but I'm explaining it a little bit better than hopefully. So, probability of A given is equal to the probability of B given A times the probability of A divided by all the ways in which A can happen. B can happen. Probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. Okay? So these are all the ways in which B can happen, one being the case of with A is true and the other being not A. And you can think about this for a second, because what this connects to is A, you can say, is the probability that that individual that I was talking about with the round P's, the F1, is big R, or not, which is then just that it's actually big R, little r. So let's plug this into this scenario. So here's our equation that we're going to plug in to this scenario. Okay. Remember, we had this individual by this individual. Okay. Cross it, got around P. Okay. Cross this to a test crosser. Okay. Just wrinkled line. Okay. And what we're going to do is we're going to imagine that there are 7 progeny. Okay. All of which bear round P's. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. Well, what is the probability now that this is in fact big R, big R? That's what we want to know. Okay. And the way we can do that is we can replace this equation by saying the probability that this individual is in fact big R, given that it has 7 big R, little r progeny, okay, is equal to the probability of observing 7 big R, little r progeny, conditional on that individual being big R times the probability of that individual being big R, okay, divided by, and this is actually sort of a proportion if you think about it. One of the ways in which this could have happened, okay, which is the way we just decided, 7 big R, little r progeny, given the condition that that individual has that particular genotype, times the probability that that individual has this particular genotype, plus another way of getting 7 big R, little r progeny, conditional now on not A, not big R, but in fact that this individual here is big R, little r, okay, times the probability that individual is big R, little r. Okay, so let's actually put some numbers into this. Okay. So going back here, okay, what is the probability that all 7 would be from this particular cross? This is the one we don't know about. What is the probability that all 7 progeny would produce this result? Okay, 7 of them. given that it's of this particular one. Well, that's guaranteed, right? Because it can only transmit big R alleles. So this is going to be equal to 1 right in here. Okay? And we already calculated the probability that this individual is big R is equal to a third. Okay? Now, if you notice something here, that this is actually, in fact, the same thing as up here. Okay? So this is 1, okay, and this is a third. Now what we're sort of doing is we're basically calculating sort of proportion of all the ways in which you can get this outcome, which is attributed to this particular condition by basically determining the ratio of this condition to all the ways in which you can get that condition. Okay, so what is the chance that you get, in fact, 7 big R little r's, 1, 2, 3, 4, 5, 6, 7, given this individual? Well, it has to happen, there's a 50% chance it happens once, and it has to happen 7 times, so it's 1/2 to the 7th. Okay? And this actually term here, as we already said, is equal to 2/3. Okay. Now, that's a little bit of a hairy mess right there, so let's just simplify it. So it's equal to 1 times a third, so 1/3 divided by 1/3, okay, plus 1/2 to the 7th, so 2, 4, 8, 16, 32, 64th, 1/64th times 2/3. And I'm actually going to simplify this a little bit to the greatest extent I can. But what you can notice here is that actually this is a small number. As you have more and more and more round bearing P's, this number gets smaller and smaller and smaller. If you actually turn this to, say, 100, this would be a vanishingly small number. And what you can notice is this term goes to 0, the whole thing becomes 1, because the sort of proportion of probability that can be attributed to this particular thing becomes more and more sort of balanced towards the condition of that individual being big R, big R. Okay. So what is that equal to? Okay. 1/3 over 1/3 plus, well, you know what? I'll let you figure it out, but you can see that it's very close to 1. And that makes sense, because we think it's very unlikely that you could have had this individual have been of this particular genotype and passed off so few, in fact 0 wrinkled P's.